I didn't understand anything, but okay, hi. Yeah, great room. I'll quickly take a picture with you. So, smile everyone. Smile. Perfect. Okay, how was lunch? Good? Yeah, so I'm Philipp. I'm from Vienna. We are the capital of schnitzels. But lunch was good here as well. Yeah, in Vienna we also do other stuff like classical architecture. And we have lots of beautiful women. Yeah, not always, but yeah. So, since I'm here, I work for Elastic, the company behind Elasticsearch and some other products. I'm in the infrastructure team, so I work on stuff like Jenkins, Ansible, AWS. We provide Docker images, all that stuff. And then I kind of pipe this infrastructure work into developer advocacy. So right now is conference season, so I'm out doing lots of conferences. So, and if I'm at home at some point in Vienna, I'm organizing a meetup about databases and one about the theory of stuff. So today we'll kind of dive a bit into theory behind full-text search and how full-text search works in general with Elasticsearch, just to give you a specific example. Okay, so who uses databases? Yeah, good, everybody. Who needs to use full-text search for their product? Okay, quite a few. Who actually uses full-text search already? Okay, who uses Elasticsearch? A few, okay. What else do you use? Solar, okay. Fair enough, fair enough. We can talk afterwards why it's a good idea or why it's not a good idea. We can discuss that. Okay, so generally, just to give you the idea, databases versus full-text search, I always explain it like this. Top up are the databases, and here we have full-text search. So the point about databases are they're very good at storing data, and then you query your data, and then you get the exact results back, whatever your query was. Full-text search is different. Full-text search is not only black and white, as you can see here, but it's much more shades of gray, so you can kind of see more stuff. And the shades of gray mean you store some documents, and then you index them, and then you query them. And you're not only looking for the exact results, so you're not just looking for an exact match, but you're more interested in the concept or whatever you're using. So everybody is familiar with what Google does, and full-text search kind of goes into the same direction. So you don't only want to have exact matches, but you more or less care about what I'm searching for and the combination of stuff. So this is what we'll dive into. So we'll at first take a look at how does full-text search actually work in theory. Then we'll quickly look at how does Elasticsearch do that. How can you interact with that? And at the end, we'll quickly take a look at how you can actually interact with that in Java. So, there's always somebody in the audience who will say, but I can use, in SQL, I can use select star from whatever, where my term is like percentage, term, percentage. So you just have the term, and whatever comes before it or whatever comes after it, I will still match that. This is a bad idea for two reasons. First off, performance. If you do a query like that with a percentage at the beginning, you cannot use an index. So assume everybody is kind of familiar what a database index in the relational world is. It's normally a B tree, so you have this tree structure. And what you do is you insert your documents there, and then you compare. And you are at the node, the root node, and it will tell you, okay, there is stuff you're searching for is in my left branch of the tree, or the right branch, or the middle branch, depending on how many branches you have. And then you have a few compare operations until you actually can see, do I find what I'm looking for, or am I not finding what I'm looking for? So if you have like 1 million documents with an index, you will probably do something like 10 compare operations just to see, do I have that entry? If I don't have an index, or I'm using a structure like this, where I cannot use an index, I will need to go through all my 1 million records and compare them one by one. Obviously, this is painfully slow, and you always need to crawl all your documents. So you don't want to do that. That is the first reason. The second reason is why you don't want to do this. Probably you're not interested in only exact matches, but like more in the concept, so you don't really care, is the word I'm looking for singular or plural? You might even not even care if it's an adjective or a noun. Or you might be interested in stuff like, I have a typo. How can I still find the stuff I'm looking for even if I have a typo? Is there any way? With relational databases, not really. With full-text search, yes, you can also search for stuff like typos. So this is while databases are useful and everybody is using them, they're not the solution for everything. So if you need a bit more power and you want to search for different stuff, you will need something like full-text search. So just to introduce Elasticsearch, it is very popular at the moment. If you're searching on GitHub, Stack Overflow, or Wikipedia at the moment, your search is going through Elasticsearch in the background. Even though you don't really see it, but it's there in the background and doing the actual hard work. So just to introduce a few concepts. So what you have in the relational world, what you normally call an instance, is just called a node. A cluster is a cluster. And in Elasticsearch, we have something called a shard, where we split up data into different chunks, and we can distribute them over lots of servers and then easily search for that, which you don't really have in the relational world, so out of luck. I think, for example, Wikipedia has 2 clusters to search for stuff, one with something like 30 nodes, and I think the other one with 20 nodes. So every time you search in Wikipedia, this is going through either one of these clusters and doing your searches. And then you have kind of, if you know what a mapping is, it's called an index in Elasticsearch. We have kind of the concept of a table, it's called a type, but it's only kind of similar, and be careful, don't overuse it, it might go away at some point in the future. Instead of a row, you have a document, since we store rich JSON documents and not just flat rows. And instead of a column, you have a field. So these are all the terms you need. And then there is Apache Lucene. Apache Lucene is actually the library doing all the searching for you. And we always compare it to a car. So you have a car, and Elasticsearch is kind of the outside. You see the car. And Lucene is kind of the engine. The engine is actually driving the car, and it is hugely important, but by just taking a quick look, you don't really see the engine. So what Elasticsearch around it provides is you have a REST interface, you have all this distribution of the data, the sharding, the replication, you have a rich query DSL, all of these things are provided by Elasticsearch. But actually what is storing your data and where all your queries are going to in the end, that is Lucene. So these are the details in the back. So what about indexing your data? The term indexing is unfortunately super confusing in Elasticsearch. In the relational databases, it is pretty clear. So you store your data and you create an index on one or multiple columns, and you simply index them and put them into a DB tree. That is the relational world. Indexing in Elasticsearch has multiple meanings. Indexing is the full process of storing data into your database. You actually have the index, which is kind of the table in the relational world. The database in the relational world. And you have also Lucene indexes, and you have all these different things called indexing, so don't be confused by them. Just think about indexing in this context, that you're storing data and kind of pre-processing it so that you can actually search it efficiently afterwards. So what are you doing when you index stuff? Why is full-text search so much more powerful than what a relational database can do? The thing is, we're doing much more work up front, so we can then search efficiently afterwards. So the first thing normally is you will remove any formatting. If you have something like an HTML string, the HTML formatting doesn't add any meaning, so you're just stripping that out. Then you have stuff like tokenizations. Tokenizations is just, I want to find my words. So I want to find each word. Normally you split stuff on the white spaces, and anything like dots, commas, exclamation marks, question marks, all these things, you just use that to split up the independent words. Then you remove stop words. Stop words are just very common words that add very little meaning to your documents, and they would just bloat the index where you store your data, and you don't really need them. So stuff like articles, whatever string you store, it probably contains an article, so there's very little point in storing an article in your index. It's just bloating the index, and you have it in everywhere anyway. And finally, you have stemming. where you can actually reduce a word to its word stem. So you cut off stuff like plurals, and you will kind of reduce the word to its basic form. This is, of course, stop words and stemming are language dependent. Works very well for English and also pretty well for German, since German is also a language easy to stem. I've been told that Russian and Ukrainian are much harder to stem and use. But there are stemmers in Elasticsearch and Lucene, and we've just in the latest version, we've replaced the Ukrainian one, so it should improve. I hope it does. We can discuss about that afterwards. So, let's take an example. So your source document you want to index is the two lazy, with an emphasis, dogs are slower than the less lazy dog, again with an emphasis, rover. So you want to index that to be able to search it. So the first thing is you do, you strip the HTML out. So, okay, you've lost the tags. Fine, that's working. Next thing is you use the standard tokenizer. This just removes all dots, commas, and stuff like that, and splits all the words into different pieces on the white spaces. So you have one element is the next is two, lazy, dogs. So you just have the independent words. Next step then is you actually lowercase everything, because you don't care about the case. If you do a full text search, as on Google, uppercase, lowercase, you don't care about that. So you simply reduce everything to lowercase. And then you remove the stop words. So in the previous example, you had the two lazy dogs, and now the D is gone. So you have two lazy dogs, were slower than less lazy dog, rover. And finally, you have, we are using in this example snowball. This is doing the stemming. So you can see lazy with a Y at the end is reduced to an I. So you could have stuff like lazy, laziness, all that stuff would be reduced down to the same word. I think something, dogs was somewhere in the plural, so you remove the plural S, you just remove everything down to the word stem, and these are now the terms we're actually storing in our Elasticsearch index. You can actually try that out. If you simply run a query on analyze, you can say, okay, this is the text I want to search. So the two lazy dogs were slower than the less lazy dog, rover. And then you can say, actually, what I want to do with this text, you can explicitly define all of these elements. So you can say, I want to have a jar filter, I want to have the standard tokenizer, and from the token filters, I want to lowercase it. You're not required to do it, but you normally do it since you don't care about upper and lowercase. Specific situations might make a difference, then you wouldn't do that. You remove stop words, and then I'm doing stemming with snowball. So you can see this is all easily configurable. There are, for most of the stuff, multiple things you can actually use instead of them. So you have some alternatives, but these are the defaults, and with them you will get what happens if you insert something. And you can actually see what this looks like if you run this. Come on. No? My battery died. No, I don't know. It's there again. Okay. So what you will get is you will get all the tokens. So for example, it knows, okay, it has stemmed away D, but 2 is the first word. And then it will actually know, okay, I've stemmed away D space. And so my offset from the start is 4. And the word ends at position 7. And the type of this is alphanumeric. And it is the first word in the full thing. So this is kind of what the analyzer will spit out if you just run the raw analyzer. You don't really need to care for it, but this is just the explanation why Elasticsearch is actually able to extract all that information. And then you get lazy, and then you get all the other words. This would be a pretty long list, but I think you get kind of the idea here. Okay, and then you actually store this in the inverted index. So in a relational database, you have the regular index, and this one is kind of going the other direction. So here you have the words pointing to the documents and not the other way around. Which one is regular and which one is inverted? There's no real rule for that. B trees are just have been around for a long time, so this tree structure you're used to, and this is therefore called inverted indexes. And then you put some metadata to all of these elements. So you normally store the term frequency, we'll later see why the term frequency is important, and the position of the word. So for each single document we insert, for example, the string we've used till now, this would be document 1 here. And then we have another document and another document. And what I would have here is the first string, or the word to, occurs one time in the document I've inserted here. And the word is actually at position 1. And lazy occurs 2 times and is at the positions 2 and 9 at my example. So you would store all of that information. And you do that for every single term. So I've just used 3 terms that have occurred in my initial document and 1 that wasn't in that one. So this here you have just occurs 0 times, no position there. So this is what you would store. And you're doing the same thing for document 1 and any other documents you have. So you will have quite a huge matrix of all the words that occur in the entirety of your documents. You have the entries for each single document or JSON. So document always means one JSON document you have inserted. So you have the details for each JSON document, and then you can easily search for stuff. For example, if you would want to know, okay, which or give me all the documents that contained to and dog, you would simply say, okay, ideally take the to row and the dog row, and I'm simply end connecting the 2 things if you want to search for both terms, and then you would have 0, so you would have for these 2 contain it once, so you have matches here. As soon as you have a 0 here, you would know, okay, it doesn't occur in that one document, so we can exclude that if you really require both terms. And why is the position important? You can also search for phrases. So you say, there needs to be, I'm only looking for the words 2 dogs, for example. This is why you actually need the position. So you can say, okay, does the term occur in a specific document and what position? And then you know, okay, and then the next term must also occur in the same document and at the next position. And so you can very efficiently search for full phrases. And you can easily end connect words, you can or connect them, and you can do very powerful queries like that. And actually, just to show you how this entire thing works, so you just use the REST interface and you put in the quotes index with the quote type, one document with the ID 1. And I simply define all the defaults here, so I'm explicitly saying the char filter and the token filter, you wouldn't need to do that. And then I'm saying, okay, this text, I'm inserting it. And then you can simply get the return, okay, I have indexed that one document with ID 1, it is the first version, this would be incremented every time you update that document, and it will tell you, okay, you were successful, and the thing was, actually, I've cheated a bit, actually created should be true here. And then you can actually search for it. So if you then post a query with, you want to search the quotes index, and underscore is always like an internal method we provide, and we simply say we want to target the search endpoint. You could limit that query to quotes quote, so you would want only to search in one type, but I don't care about the type in this example, so I'm just searching for quotes search. You could also skip the quotes and search over all the indexes in your Elasticsearch cluster, so you can do that as well. So here I'm just doing search, where I have a query with a match for text dog. And what you would then get back, you would get the document, it would actually tell you, okay, this was the document you have indexed, and you have a score of 0.25. So this is the quality of your search result. We'll come back to the score because this is actually how the relevancy or the quality of your results work in Elasticsearch. So this is all pretty nice and simple. We've inserted our stuff, you can easily search it like that. It's a bit slow today. Okay, and if we would search for lazy, we would get a higher score because lazy appears multiple times in my string. So what does this score actually, how does this scoring thing works? This is what makes full-text search also very different to relational databases. So the formula for scoring, how it is implemented at the moment is you have different components, you sum up a few attributes, and then you provide a query norm and a coordination, and this will give you that score value. So this is just a numeric value. There is not much meaning comparing that between different queries, but it will, with a very good quality, rank your document within one search query. So this is just a numeric value between 0 and more to give you back results. So, how does it work? And yeah, this is just a disclaimer on the side, like in the next upcoming version, we are switching the default scoring mechanism to something more complex. But we'll stick with the simple example today because this is also the most common approach. So the first thing you're interested in is the term frequency. The formula for the term frequency, you just have a term over all your documents, how often does it occur, and you then calculate the frequency out of that. What does it actually mean? If a term occurs multiple times in one document, that document is probably more important than if the term only appears a single time. So what this would look like with the current implementation is if a term occurs 10 times, you can see on that axis here, it's probably 3 times as important as if the term was only occurring a single time. So this is how the term frequency works. The more often the term appears in a string, the more relevant that string is for you. The other thing is the inverse document frequency, where you calculate, okay, if I'm searching for multiple terms, one of them might occur in many documents and the other might occur in very few documents. So if I'm searching for these two elements, the one term that is occurring less often is probably more relevant for my search. So the less common terms are more relevant, which will look something like this. The more often your term appears, the less relevant it is. So this is the inverted document frequency. Frequent words are kind of less important. This is the message. And then you have the field length norm, the normalization part, where you actually assume, like, if a string is very long, a lot of words will appear in it. So each of these single words is not as relevant as if you have a very short string and a word appears there. So if you have a short title and a word appears there, it is probably more relevant than in the full paragraph or even multiple paragraphs where you have lots of words. Then each of these words has less weight than it would in a short one. And then finally, there is the vector space model. If you want to match multiple terms, how do you make sure, like, how to weight them or how to find the difference if only one of your terms appear? So what you do is you calculate the score for each of these documents and then you create a vector to actually compare the stuff. So what we're doing here is we're searching for happy hippopotamus and we have 3 strings we're searching. So you're first searching, I'm happy in summer. After Christmas, I'm a hippopotamus, and the happy hippopotamus helped Harry. So which of those do you think will be the most relevant one? The third. Which one will be the second most relevant one? Yeah, this will depend on your overall documents, but assume we have lots and lots of strings, and I assume in most cases happy will appear much more often than hippopotamus. So the word which contains this here is then probably more relevant than the happy, because happy is just super common. And just matching happy doesn't give you so much. So how does that actually look like? Unfortunately, we can only visualize that easily with 2 terms. But if you have more terms, you would just have more dimensions. But this is just a 2-dimensional model, which is very easy to display. So since happy is very common, we just assume it has a weight of 2, but hippopotamus is not so common, so we assume its weight is 5. And the combination of these two is 5, and 2. And then every document you can actually put on that scale here. So for document 1, which contained only happy, so you had 0 hippo, but full happy, so this will end here. And for the string that only contained the hippo, you have 5 here, but 0 on the happy axis. And if you have the third document, which contained both terms, it will land here on 2, 5. And this is the same as the actual query. And then you can calculate how big is the difference from the angle here. And the closer the angle is, the more similar your search results are and the more relevant they are. So you can see the angle from happy is bigger than from hippopotamus. So this is a perfect match. This will have the highest weight. This will have the second highest weight because the angle is lower. And here you have the highest angle, so this is the least relevant word. And this is how the vectoring works. And with more than 2 words, it gets more complicated because you just add more dimensions, but the general idea is totally the same. So this is how all of this scoring then works. Okay, so just to give you a little more example, we've done that. So we'll just use another example to run a few queries to see what is going on. So let's assume we have movies. We have The Godfather by Francis Ford Coppola, written or appeared in 1972. We just put that into our database, so movies, movie 1, we are storing that. And it will tell you, okay, I stored something in the movies index from the type movie, first version of that document, ID 1, and version 2 in that case, and I've stored that now. So if I want to run that, I can simply get that ID. This query is very similar to what you would do in a relational database. You simply know the ID, and you simply do a match on that ID. And you can see I have all different stuff here, but I don't have a score, because there's nothing to score. You're not comparing any values, you're just retrieving a document. This is what you would do in a regular database. Next up, I can simply show you how the mapping works, because Elasticsearch is often advertised as mapping, free, or schema-less, but actually there is a mapping. It can just be created dynamically, and when I insert a document, it actually will appear. So the mapping looks something like this. You can see you have director here, one of the attributes we inserted, and this is of the type text. And it will be inserted in my index, but only the first 256 characters. The rest I'm throwing out, not to blow up my indexes too much on that one. So this is how the mapping looks like. This is just kind of, again, the background information, but you don't really need to care about that. Only if you go to production, think about your mappings, because you cannot change an existing mapping once it has been inserted. You can add new attributes, but you cannot change the types of existing attributes. You will need to reindex your data, and that is very painful. You don't want to do that. But I can update stuff. So I can simply add to my existing document. I'm adding crime and drama, the types kind of my movie. So if I run that, it will be created again, and I can run it. And here again, yes, I'm getting in source _ source. This stores all the original elements of my document, so I can simply retrieve that. As long as you use it like that, it's just like a regular database, what you would expect. But we want to do some more stuff. For example, we could filter something. So here I'm running a filter query, and I only want stuff from the year 1972. Okay, I have just a single document, so the result is pretty expected. But I'm running this, and here I have a score of 1, because I have just filtered down on one term, and I get the results here. The thing about filters is, with filters you don't actually calculate the score. You just take one element and you do a direct match and get everything back you want to have. So you cannot only get stuff by ID, but this is just like a where clause. So you just say select star from movies where year equals 1972. So this is very much like a database operation again. Now we actually want to jump into searching. So I have a search query here, and I say my query with my query string, I just want to query all the fields. I don't care about which field. I just want to search for Ford. And if you run that, is that still big enough? Here it will tell you, okay, I have matched something with this score, and yeah, this is the document, and it will find that for you. You can expand that a little and actually say, I want to search for the terms Ford and Godfather. So you will probably only find one of the movies or you want to have this movie the highest ranked one. Remember the score, 0.3, and if you run that query now, the score improves for that one, because now we have two terms and both of them are matching for that document. If you had other documents and only one of these terms would match, they would have a much lower score. So scoring is at work here, and thus just what we have discussed before. So this is how the ranking then works. And you can do stuff like incomplete searches. So even though that breaks pretty badly here. So this would be like in the relational world, if you did just a where like for a percentage sign, you can just use wildcards. And this is still pretty efficient in Elasticsearch. So you can just say, give me anything that starts with 4. You can, of course, put the filter also before it. But where stuff gets much more interesting is if you're like me and you can never remember how you spell Coppola, and you just spell it wrong. So if you have Coppola with 1 P instead of 2, and you say, but I'm not really sure, so I just want to fuzzy match that. And this you definitely cannot do in a relational database anymore. You will need some form of full text search, because if I search that, again, I'm matching on one term, so this is fine. And I'm still matching on Coppola, even though I have actually mistyped my search query. So I can tell my queries, if I remove the tilde, it wouldn't find anything. So nothing matches Coppola. So then I might think, okay, maybe I've just mistyped it. I'm adding the tilde again. I run it, and then I find something. There is a lot of fine-tuning, how you can do stuff like partial matching and stuff like that. But the general idea is you store stuff in Elasticsearch, and then you can also do fuzzy matches. One common approach for that would be n-grams. So you split up one word into groups of words, and you would do the same thing for your search terms, and then you try to find many matches, like how many groups of words do you match. So you would, for example, if you had Coppola, you would could use an n-gram of the value 3. So you would take the first 3 characters, you would index that. Then you take the next 3 characters, you index that. Then you index the next 3 characters and index that and all of that. And then you split up your search queries again in the same manner. And then you try to find the stuff where the most 3 character n-grams are matching from your index to your search queries. And this is how you can very efficiently still do fuzzy searches without going through all your documents and searching for something. And at the end, just to clean up, we can delete the index, which is very easy. It will just tell you, okay, acknowledge true, thank you. And after I query it again, nothing is found. So this is done here. Okay. So, who uses Java? Who is asleep? Okay, only one person, good. Holding up well. So who uses JPA? Okay, a few. Have you written something like this? Is this okay? Yeah, maybe, maybe not. So I'm always thinking like the relational world and the object-oriented world don't match so well together. And again here, this is true for Elasticsearch, but anything else that can store JSON. So this would be true for MongoDB, CouchDB, Couchbase. Anything that stores JSON, I think, is geared much better to storing your objects than a relational database. So we'll quickly take a look at A, how can you interact from Java with Elasticsearch in general? And B, how can you jump over this impedance mismatch? So you have two different concepts that don't really match together so well. Okay. So there's also this saying about that Ted Neward said, ORM is the Vietnam of computer science, because it's just like a never-ending clusterfuck that, yeah, you at some point you're just being stuck, and then you have a few hard choices to make. So you can either then abandon object orientation, you can abandon your relational database and just serialize stuff into your database, and all these decisions. His post is 10 years old, but it's still partly valid. Some stuff has improved, but still, if you're using JPA, Hibernate, all these things, you're probably aware of that. Yeah, it's very easy to get started, but it's often not really giving you the best performance or really all the power of the underlying system. Okay, so let's take a look at Elasticsearch and the Java driver. So you can just use our X content factory and build your JSON objects. And then you can say, okay, I'm starting an object, I'm sticking with my movie example here, and I have a field title, a field director, a field year, and then I'm adding the attributes, and then I have a sub-element. So I start an array and put in the values I want to store into that. And yeah, is this nice? Because when I suggested that to my working colleagues at my previous company, they were like, nah, we're not really going to use that, right? Because this is not the way we want to interact with a database. So, what else can you do? One common example would be Spring Data Elasticsearch. Just a disclaimer, Spring Data is, yeah, Spring ecosystem. Spring Data Elasticsearch is actually not maintained by Spring and also not by us, but this is community driven and community developed. So the two main developers are actually based in London. I was in London this week, so I met them for a coffee and we had a nice chat, and yeah, they're working on it, but it is community driven, so don't expect any stellar support. It's just they're doing it, I think, in their 10% company time and in their free time. It is working well for many, but it is not a paid product or anything. So what you have, instead of object relational mapping, you have object document mapping. Since you don't have relations, it's just documents, and they call it ODM, or like mostly in that space it's called ODM, and you don't care about relations, so you just have documents. And then you have your plain old Java objects and a few annotations, and you can easily search that stuff. And who's actually using Spring Data? Just to get an idea. Okay, lots. So many of you will know the repository approach. You have you register your repository, and then you can use that to interact with your data store. So how does that look like to work with it? So yeah, you add the dependency. To add with the current stable version, you will need version 2 of Spring Data Elasticsearch. And then you can just slap a few annotations on your Pojo, and you're good to go. So for example, if I have my class movie, and I want to say, okay, the index name is movies and the type is movie, I have my attributes, my ID annotated with that ID, and then I can say, for example, director is a string, and it should be analyzed, and that thing should be stored. So with add field, you can actually configure how stuff is treated. What the analyzed thing is doing, you have two options. You can either say, I'm not analyzing anything, then you can just do exact matches like in a relational database. Or you actually analyze a field, then you have the stuff like stemming, stop words, fuzzy matches. So this one here, in this example, I'm saying my director should be fuzzy matchable. And yeah, I'm storing the other stuff, and I'm skipping the getters and setters. So how this would look like if I then insert something is I create my new movie with my ID, I set my attributes, and then I save my movie. And yeah, if you think this is not so nice, use Lombok. There's a talk later today about Lombok by Vladimir in the last time slot. Unfortunately, that is competing with my second talk about Elasticsearch, but yeah. I'm a nice guy, I'm still advertising his talk. So if you're interested in Lombok, I think he's in the upper room. Yeah, final time slot, Vladimir. I'm sure he will do an entertaining talk. Okay, so repository. You just register your repository. You say, I have my Elasticsearch repository, and I extend that to create my movie repository from type of movies, and my IDs are strings. And then I can simply say, find director's name. I provide the director's name, and is this pageable? And then I can simply search for stuff. So if I have, I'm just putting in the full string here, but I could also just put in partial string, and I'm just paging through it, and I'm just requesting the first 10 films Coppola directed. And then you can page through the result set and just retrieve data. Looks very much like a relational database. You can use you can do pretty much all of these features, but you can then do also fuzzy searches and all the analyzed stuff you want to use. And the other thing is polymorphism. So if you have, coming back to this impedance mismatch, if you have an abstract base class with an employee, with one attribute, and a manager and a worker, so the managers can, in addition to the name, they can approve funds, and the workers have experience. Managers obviously don't have any meaningful experience. You want to store that. And with relational databases, you have three options. First, you can use a union table. So you put in everything into one table, store it, and you have potentially some null values. With two implementations, and each one of them has one attribute, that's probably fine. But if you have more specific implementations and many attributes, you will have lots and lots and lots of null values, which is kind of against the idea of a relational database. If you have more than half of your attributes are null values, you have more of a Swiss cheese than an actual relational database. So we're looking for another solution. Second would be you create concrete instances without any common queries. So you just have a table of workers and one of managers, and you can query each of them, which works fine unless you want to get all your employees. Then you will need a union clause. Yes, this works, but it doesn't really match how you structure the stuff in your object-oriented program. So you can feel there is this mismatch. And the final option would be you create a base table, you have an employee, and you have these two specific implementations. So you have a worker and a manager, and whenever you query a worker or a manager, you would need to join that record with the base table. So you always have a join. Again, it works, but it's not really matching as well as it could. So yes, it feels kind of painful, but Bob probably can take the pain away from you. So this is what you can just do with Elasticsearch here, or you could do that with anything that stores JSON. So you have your base class. In this example, I would simply say, okay, I just create two different types, because that's fine. Both go into the employees index, and I just use two types to store it. And I just have the actual JSON document with all the attributes stored there. No null values, no joins. I mean, there are no joins in Elasticsearch, so you cannot do them, and you don't really need them if you structure your stuff correctly. So this matches much nicer. Okay, to conclude, search is super powerful in Elasticsearch, and I haven't gone into too much detail about these attributes, but you can define like must not. These are pretty simple, and you can do that with a relational database as well. What you cannot really do is should. So you can say, I have something here, and it should match. It's not a problem if it doesn't. The must will include or must not will include, be a hard constraint, exclude everything that is not matching or not matching. The should is like, yeah, it would be nice to have this attribute. So for example, you often have on websites the search when you're shopping, you can define attributes, and you can just say, okay, these attributes would be nice. They are not a requirement. I still want to get results even if nothing is matching. But if there is matching something, I want to have these results first. And this is exactly what Elasticsearch can do. And you can provide multiple attributes and say, okay, this should match. And if something matches all three of them, it will be the best match. If something only matches 2 or 1, they will be lower in your results, but they will be there. And you can define stuff like, from my shoulds, at least 2 of my 3 shoulds must actually match, otherwise I don't care for the results. So you can write pretty powerful queries. Second thing you can do is you can write filters. There you don't have any proper scoring. It's just like, these are again hard requirements like the year. Only give me the films from the year 1972. And you can do very powerful aggregations. So pretty much anything you can do in the relational world with group by, sum, average, all these things. You can do that and much more powerful stuff in Elasticsearch again. So you have, we call it buckets and sub-buckets, so you can split up stuff and you can easily group that and visualize it. So one example would be you have people and then you can define, okay, give me all the people split the people up by country and then split up the countries by city and then split them up into other attributes. So you can do very powerful aggregations which you cannot do with many other NoSQL solutions. Then this is the common question like, but is it fast? And our answer is always that it depends. And you will not need to write your own prototype because like you can see, Professor Zipinski here has tested is the squid more intelligent than the house cat? And yeah, in this example, the squid is much more intelligent than the house cat, but this is not really what you replicate or what you wanted to test. And there were these examples where people run benchmarks. So some of our competitors always do benchmarks against each other, and everybody manages to be the fastest. Even if two competitors benchmark against each other, each one of them will be able to find some scenario where they are the fastest. So this is not really helpful. Stuff you won't get, I'm just saying, you then don't get multi-document transactions, you don't get joins, you might not need joins if you can structure everything correctly in your JSON documents. But you will get is you have pretty rapid development, you have very powerful replication and charting out of the box, and you don't have the impedance mismatch, but you have an impedance match with rich documents and rich queries. And to sum up, Elasticsearch, developers mostly love Elasticsearch, and I've heard even the minions love Elasticsearch. And if you want to know more about the stuff we do, so this was just Elasticsearch, one of our products. We have a few more, mainly for logging and analytics. I'm going to talk about that on track 2, shortly after 6. So the full Elastic stack with all our products, I'll demo there. So, I think we have like 1 more minute, or are we out of time? Okay, any questions? And I have some stickers here. If you want to grab stickers afterwards, just come here, grab whatever is left. So, questions?
Hi. So just curious, how fast are the writes in Elasticsearch? Is it like 10 milliseconds or 100 milliseconds? So what time it takes to index the document? And in terms of Elasticsearch, what can make your inserts faster or can make them slower?
First, it depends. And second, so we call them near real time, in contrast to a relational database where everything is more or less instantaneous. In Elasticsearch, you will have a very short delay, but I cannot answer that in 1 minute because this will include some more background. We can talk about it afterwards. Normally, you will have 1 second delay, but this is configurable. Depending on your use case, you could also decrease that value, but there is an overhead you need to pay for that. Normally, the 1 second delay is fine for many use cases. Also, like full text search often only is required. Like if there's 5 seconds delay, that is fine. But it's a configuration option. There is normally a 1 second delay. And for some use cases, people even increase that value because it will make writing somewhat more efficient if you don't need to write that often. Yeah, it has some background implications we can talk about.
By the way, are there any like batch insert or some batch import of the documents into the...
Yes, there is a batch API.
Oh, okay.
So you can simply say I have, I don't know, whatever document number, and you can then define a batch size, and then you can just shoot your documents in big chunks over, and they will be indexed, yes.
Thanks.
Batch API is what you want.
Is there any mechanism of automatically updating Elasticsearch index while DB is updated? Like what? Data in DB is updated and index is updated too?
So you cannot change anything. You can add new attributes, but you cannot change an existing mapping.
No. So you index a database once, and after that we are searching. And after that database or some data source is updated. How we update index?
You mean you want to replicate the changes
yes.
from the relational
yes.
database? Your best bet is normally from within your application, because then you have fine-tuned control. We provide some solutions, but so you can just have a process running and that will check your relational database every second, and it knows everything that has been inserted so far by whatever ID you provide, and then it can just grab everything that has been inserted into your relational database within the last second and copy that over. Or if you have a timestamp field, it can simply say, okay, last time I checked was this timestamp, give me all the data that has changed since then. So you would get both inserts and updates and copy that over. What you normally don't get with that solution is deleted entries. So this is why it, for many solutions or many cases, it is advisable to do that directly from within your application. So you write through the relational database and you explicitly write to Elasticsearch, so you have more fine-grained control.
I have a question about synonyms. Namely, we had an issue of explicit mapping of phrases to words abbreviations. For example, you have OB, which stands for online banking, and your customers might search banking online or online mobile banking. Can you control tokenization and phrase swap on synonym lists with Elasticsearch?
Sorry, once again, what was the end?
Can you control tokenization rules, phrase swap, and other basic parameters
So
queries for synonyms?
So you have very tight control. So you can define your own synonyms first off. You're probably doing that already. And then, yes, all of the steps that are taken can be turned off, turned on, and you can either add other implementations that are available, but you can also write your own implementations if there is something you don't have. It's not so common, but it's actually not that hard. You don't need to change so much code if you want to have your own implementations of something in that whole analyzing, tokenization, stemming process. So you totally can do that.
Thanks.
Is there a way of customizing score number? For example, one vault has been much more score than other.
Why would, I mean, yes, there are, I didn't talk about it explicitly, but you can actually boost stuff. So you can say, for example, one field is more important than another field, so you can use boosts. And so Elasticsearch is also used for recommendations. And sometimes recommendations can go terribly wrong. I think we've had a use case from some online shop, and they sold different stuff. And then people started buying sex toys. And whenever somebody, and because this thing learned like what has been bought, and then whenever you searched for doll, and you just wanted a kid's doll, it would suggest adult dolls. And then they had to negatively boost some of these terms. So yes, you can do stuff like that, that you can fine-tune your scoring. Sometimes it's a good idea.
I have a question about an index engine in the Elasticsearch. So the main point here is, does the Elasticsearch provides us some type of engine which can give us an ability to build our indexes asynchronically, like the MongoDB does? As you know, when I'm going to create an index, I need to log the whole document. So can we create any indexes without the locking all of the documents?
Locking works very differently than MongoDB.
Yeah, but...
So you're having a specific problem in Elasticsearch, or you're just comparing it to MongoDB?
No, just to know if the Elasticsearch can provide us the asynchronous mechanism to build the indexes.
So a write operation itself from the client's perspective is synchronous.
Yeah.
And the replication is by default, I think you can change that, also synchronous. So you will go to one node and then probably to the replication, and you wait for both of them to apply that. But you're not locking anything inside the storage engine, because you have all this indexing and you just flush it to memory, but it is actually one of these so-called segments. A Lucene segment is only by default written out once a second. That was the other question about the segment, the write delay. So this is working differently. You don't, in MongoDB, yes, you're locking depending on your storage engine, your either locking your previously the entire process, then only the database, now only the document with wired Tiger. That is a very different concept. It doesn't happen like that. Also because like Lucene under the covers is working differently than MongoDB does. So this is not that issue that you're locking your entire thing and then you're blocked.
Okay, thanks.
We're out of questions. I assume we're also out of time. So thanks a lot.